realized, and now we're recording. So let me back up. Basically, this is just saying that quantum physics is not necessarily an active area of science. It's now, besides being that, it's also transitioning into an active area of technology because of its unique applications that we are now capable of trying to realize. So first, you in a quantum technology, you identify and understand interesting quantum mechanical effects. For example, stimulated emission. Realize these effects using available quantum technologies. So this was done using the Ruby. So the laser was the technology that basically was a spin-off from stimulated emission. And often these technologies don't have applications right off the bat. And this was remarkably, to me, true for the laser as well. The laser was a solution looking for a problem. At least it was called that back then. And of course, we know that's not true anymore, because the third step of the evolution of a quantum technology is to develop technologies based on the effects, the realized effects that have potential applications to the real world. So we know that's definitely, the laser has fully realized this third step. By the way, I may have trouble hearing you because it seemed the audio was cutting in and out. So just if you're not getting my attention, feel free to just chat. So there was a wave of quantum technologies started a long time ago, maybe starting 70 years or more, that I guess I can group into something called quantum 1.0. And this dealt with basically three types of quantum particles: photons, spins, and electrons. And their associated fields were I name in these three columns. The laser clearly was, I think, one of the key applications of quantum optics, which of course led to the applications I've mentioned in the previous slide. Nuclear magnetic resonance and the probing of spins as now forms the workhorse of many quantum devices, but an older technology that it fostered is magnetic resonance imaging, a very key medical technology. And the quantum physics of electrons has yielded the transistor, which, you know, we wouldn't be meeting and talking like this today without, because it forms the backbone of basically almost all of electrical devices that we use today. But that's not all. There's now been I guess a new, relatively new, maybe 20, 30 years push into a set of quantum technologies that one could group as quantum 2.0, second quantum revolution, to borrow from Bill Phillips' talk. And the main push, not the only push, but the main push of this set of technologies is, of course, building a quantum computer. Because of, Shor's algorithm highlighted that a quantum computer is capable of solving certain specialized problems, specific specialized problems, significantly faster than an ordinary computer. So as I said, this is not the only push, or not the only member of this set. Starting from probably the early era of this quantum 2.0 era, or the early times, were efforts that that developed ways to control small quantum systems, such as ions in a trap or photons in a cavity, and have atoms interact with these photons. And this ability to control these quantum systems in a very fine-tuned and precise way led to a renewed push to simulate large quantum systems, to scale up these small quantum systems and use them to simulate other systems that are not readily available in nature that we would like to better understand. This, I think, was a key seed in this quantum 2.0 revolution. It led to 2 Nobel Prizes, one of which has a winner who's now our colleague, Bill Phillips, who won the Nobel Prize in '97 for being able to trap Bose-Einstein condensates. Now, in another direction, people have very quickly realized that quantum phases of matter may, in particular, quantum computers that are robust against, intrinsically robust against noise, but other areas as well, for example, robust currents on the edge of materials that could be useful for quantum switches or the other electronic devices of the future. And there was a Nobel Prize for these unique quantum phases of matter, in particular topological phases of matter, that was shared by 3 researchers in 2016. And I guess here I want to highlight that besides the stuff you're taught in school doesn't really apply here. There are way more phases than a solid, liquid, and a gas and a plasma in the quantum world, and people are still working actively to classify and characterize all of them. As another application, people have realized that one could try to use these small, finely tuned quantum systems to sense sense anything from biological molecules to enemies hiding underground to oil, etc. And this has quantum sensing that I think is one of the more near-term viable fields, applications of quantum effects today. I'm quite excited by some of the things that this field is developing, including here, for example, sensing magnetic fields in biomolecules. And of course, last but not least, quantum effects allow you to communicate in a way that an eavesdropper would automatically be detected. This has to deal with basically this fundamental idea that somebody observing a quantum system will collapse it and modify it. And this has led to the development of quantum communication protocols that are inherently secure, as well as ways to distribute quantum entanglement over a quantum network. So together, these 4 applications form this large field that I'll call quantum science, technology, engineering, and mathematics. That's at the sort of overlap point between many different conventional fields today. And that's what makes it really fun, because you can talk to any members of any of these fields and really absorb their unique perspective and try to synthesize them into developing these quantum technologies. And I think this is a necessary thing. So we need to work together, because these effects, to really go through this pipeline of identification to realization to manifestation in an actual useful product, we really have to include everybody here. We can't leave anybody behind. So where are we today? I'll briefly do that here. There was a term coined by John Preskill called nist. This is kind of where we are. There's several technologies that are now at the forefront of trying to scale up these small quantum devices that I mentioned before. My internet might be unstable, so I'm going to close my video. The one of them that's being actively studied by several companies as well as universities is superconducting qubits. There's, of course, trapped ions, and a more recent player has been the Rydberg atoms that are trapped using optical tweezers. And there was a recent paper by the Harvard group of Lucan and company that I think realized a 250 qubit quantum device. Now, I don't mean to say a quantum computer, because not all of the devices that are realized using these technologies at this time can realize a universal set of gates, much less have those gates be precise enough to really render a 250 qubit quantum calculation. Nevertheless, it's pretty exciting and daunting that the numbers that people are reaching nowadays. But we have to be honest in front of to ourselves and others that this is actually very hard. and there may be ceilings and roadblocks that we will hit and we have to overcome. So another promising quantum technology that hasn't yet been sort of fully coming to fruition, but is definitely an effort that continues to be worth investigating, is topological qubits. And of course, I don't want to leave out any other efforts, because this time is an exciting time, in that any one of these can come ahead and overtake all the others, and it's not really clear which one will come out the clear winner. I believe, from what little history I know, this was a different in the classical computing world, where there was more of a clear blueprint of how to scale up a computer once they've figured out the transistor. So this is a very fun time and a very fun playground, especially for theorists who can try to develop any one of these technologies, either more on the applied front or more on the abstract or theoretical front. So the UMD quantum ecosystem, what this talk is all about. So I've found that there are 7 quantum centers that UMD has that are active at the moment. There are 4 what I called quantum adjacent centers that I'll mention, and 1 startup foundry that basically, from what little I know, is some sort of an incubator for quantum startups. Maybe somebody else can elaborate on what the startup foundry is, but I want to mention it here. In total, there are 101 faculty spread out all over UMD, and in all the departments of all the classical sciences that I've mentioned in the previous slide. They're split between 45 theorists and 56 experimentalists. The UMD quantum ecosystem is itself part of the Mid-Atlantic Quantum Alliance, previously the Maryland Quantum Alliance, which is an even larger conglomerate of schools and I think companies and government labs. And most excitedly, I want to share this very recent news that UMD is now leading a $25 million NSF grant effort called the Quantum Leap Challenge Institute. And if you thought we didn't have enough centers and institutes, we have another one that we are spearheading called the Institute for Robust Quantum Simulation, about 3 days old or so at the moment. And so this is a very exciting time. Lots of funding has been pumped into the system, and we look forward to trying to utilize it to the best of our abilities. So the 7 quantum centers, what are they? Let me briefly go through them. The Joint Quantum Institute, is probably not the oldest one, but it is probably the one most associated with the quantum technology aspect of qSTEM. And its goal is to lay the foundation for engineering and controlling complex quantum systems capable of using the coherence and entanglement of quantum mechanics. I think that's one of its goals. A related institute, 1 floor above the Atlantic building, is the institute I'm a part of, the Joint Center for Quantum Information and Computer Science, which focuses on advancing research and education in quantum computer science and quantum information theory. So I would wager to say it's significantly more theory-centered than the JQI is. The JQI, I think, is more experimentally centered. However, there are theorists and experimentalists on both institutes at this point. Now, I mentioned there was a materials application in Quantum 2.0, and of course, there's a very large quantum materials center. One of his goals is to establish to be an interchange of ideas and skills among scientists working in all aspects of condensed matter physics and quantum materials and phenomena. This center is, I believe, in close partnership with the Condensed Matter Theory Center, whose goal is to basically pursue top-tier condensed matter research on all fronts. So these are sort of the materials aspects of Maryland. Another adjacent quantum sphere is high energy or particle physics, which is represented by the Maryland Center for Fundamental Physics. Now, the reason this is also a center that I firmly believe is in qSTEM is because there are many quantum simulation. There's many avenues to simulate these quantum systems that are of interest to high energy and particle phenomenologists, and several faculty in the center are actively pursuing such efforts today, and therefore overlapping with us at QUIX as well as those in JQI. Now, on the more applied front, there's been two new quantum centers. One of them is the Quantum Technology Center. And loosely stated, one of its goals is to have a global impact creating translational technologies and addressing some of society's toughest challenges. This center aims to sort of be more of an applied and more to the sort of tailoring to the third point I made about how quantum technologies evolve, namely actually realizing and producing useful product out of these quantum effects. There was a question, what is UMD / my definition of institute or center? I would say, for me, a website with missions, with some sort of a coherent about statement and people that are members of it. Yeah, somebody else raised a hand. Well, you can interrupt me, I'll just keep talking. And more recently, there's now been a qubit collaboratory center, or sorry, just a collaboratory that's been started whose goal is to pursue disruptive fundamental research and enable technologies with a focus on qubit development for quantum computing and other applications such as sensing. So these are the 7 quantum centers that I'm relaying here. So there was questions. Can anybody want to unmute, or do you want me to? I don't know if Amanda has permission to. I think we need to promote her to speak. Yeah, I'm asking her to unmute. She's muted at the moment. Well, okay. In the meantime, yeah. So, this this LQS Qubit Collaboratory is sponsored by the Laboratory of Physical Sciences, which is one of the external centers. It's external to, well, semi-external to Maryland centers that I'll mention in a bit. And I think it's the newest technically center that we have. Okay. There are 4 quantum adjacent centers. Here they are. The first one is the University of Maryland Institute for Advanced Computer Science. This one has basically manages us at QUIX. And it has people that are interested in quantum along with people interested in AI and machine learning, deep learning, etc., and other computer science topics. Institute for Physical Science and Technology. Of course, it also has a few quantum qSTEM people, along with members of chemistry and I think biology departments as well. There's also the Institute for Research in Electronics and Applied Systems, along with the Maryland Nano Center. I think they have some overlap with the Quantum Materials Center and experimental research in that along those lines. There are 4 government institutes that are helping fund these large-scale efforts at Maryland. One is NIST. So I'm an employee of NIST. There are several of us sitting in QUIX, and just to clear it up, we are basically regular faculty from the viewpoint of students. So you're welcome to work with us and chat with us. And just like regular faculty, will be just as hard to catch and in terms of answering to emails. Now, the second government institute is ARL, Army Research Lab. That's also nearby here. And there are two NSA-funded institutes, the Laboratory for Physical Sciences and the Laboratory for Telecommunication Sciences. And LPS is the one that's responsible for spearheading this qubit collaboratory that I mentioned recently. I believe LPS also helps out with QUICS along with NIST. And I probably am omitting all the different ways that these government institutes help the infrastructure at Maryland. So I'm sorry about that. All right, so let me get into some of the faculty. Now here is meant to be more of a discussion. If there's something here that you wanted to add, feel free to raise your hand. So I've basically corralled all these 101 faculty members. Here I'm going to take 45 theorists and I'm going to organize them into subfields. The subfields have been curated by some of us, but there's definitely more room to tweak. First is quantum complexity theory. So quantum complexity theory is a field that basically characterizes how much quantum memory and time it takes to solve families of computational problems. Just like normal computational or classical complexity theory, it organizes problems into coarse-grained complexity classes, which are now using quantum resources as opposed to classical resources. And here are the faculty that are involved in this field. This is very quick-centric, this particular field. And I want to say, I guess I should change here that Daniel Gottesman has actually joined us and is online now. Quantum algorithms. So as opposed to classifying and characterizing sets of problems, these researchers actually develop algorithms that solve those problems and that are run on a quantum computer in order to solve instances of hard computational problems. And of course, the key goal is to identify problems and develop algorithms for them that require less time and or memory resources than the best corresponding programs running on a regular classical computer. And here are the researchers in that subfield. Quantum cryptography, switching to the sort of communications front. So here the description is that quantum states can be communicated over distances. And as I stated before, anyone attempting to eavesdrop on such communication will cause the state to collapse, thereby revealing themselves to the communicating parties. This is probably a very basic explanation. There are, of course, other more intricate protocols that people are developing. And here are the people that are working on that topic at Maryland. Now moving on to the statistical physics front, you can recall that classical thermodynamics studies how to describe a system using emergent macroscopic quantities. So now we're dealing with very large quantum systems that you don't throw over on a fiber, but you just have them sit in a room and you try to understand them using some macroscopic properties such as pressure and temperature. And you also want to probe them with light, etc., magnetic fields, and see how they respond to these changes. So quantum thermodynamics studies how similar quantities can emerge in a quantum system, both large and small. And the field of open quantum systems studies interactions of quantum systems with their environments, including on the applications front, how to engineer environments that help a system perform interesting and useful tasks, such as quantum gates in a quantum computer or stabilizing some exotic phase of matter that's not readily available in nature. So my thesis is on open quantum systems. Quantum error correction. Quantum systems are fragile, and so they'll inherently collapse when observed by this environment. We may not have full control over the environment, so we just have to deal with this. And the way we figured out how to deal with this is to create protocols that allow you to detect and correct against quantum errors caused by the environment. So it's a study of how to protect quantum systems from detrimental effects of noise. And we're excited here. The newest member here is Daniel Gottesman, as I mentioned, who's already joined us. Paired with quantum error correction is something called quantum control, which is a field that's generally concerned with controlling quantum systems using the available tools. So usually this problem is phrased in a way that you're provided some fixed way to probe a system, and you want to figure out how powerful this way is and what you can do with it. And Of course, we have to take noise into account, which makes this problem very, very difficult. And so here are people that have been interested in quantum control at Maryland. Now, AMO physics is more of the traditional fields that's inherited by us from quantum 1.0. Researchers in this field study the interactions of between light and small scale quantum systems, such as atoms and molecules. This field has seen a resurgence due to the advent of quantum technologies. In particular, I've personally seen several different effects that were not able to be realized in optical systems, now being realized in microwave systems and other technologies today. This is a very large field with lots of overlap with people from all the institutes. Paired with AMO, I guess, is very related, quantum sensing. This is a field concerned with using quantum devices to detect quantities of interest. I guess I already mentioned MRI. LIGO is, in a sense, using quantum sensing. And theorists in this field study things ranging from abstract characterizations of the limits of precision measurement to more applied things like helping experimentalists develop measurement and sensing techniques using devices that are available at hand right now. Going back to large quantum systems, this is a field that's concerned with how to understand them. A quantum system, even a small one, has lots of different effects that are not very intuitive. Combining these things and inducing a notion of locality on them is a whole nother can of worms. If you want to also consider electrons as opposed to bosonic degrees of freedom, then you get more effects. So theoretical understanding of properties of such systems, this can be analytically, like in the study of quantum spin systems, or computationally, like in quantum materials and computational materials science. This is a problem of enormous importance. And there are many different people that are studying this from many different points of view. Its close cousin is condensed matter physics, which focuses on the many body systems that comprise quantum matter. So I would say, loosely speaking, gapped quantum systems, so ground states of gapped Hamiltonians is a big set of quantum systems that people study in condensed matter physics, but not the only one. And one key aspect here is to organize this large set of gapped quantum systems into different phases. And a key application of this, is realized by Kitaev a while back, is that some of these phases can be used and underlie blueprints for fault-tolerant quantum computers. And going to that specific area, those phases are called topological phases, and they can be studied both from the condensed matter viewpoint as well as from the quantum information viewpoint. And the sort of loose set of researchers that try to straddle both of these ways to understand these systems, I've grouped in this on this slide here. So this is, as I was saying, an intersection of condensed matter physics and computer science. We try to study such phases both for intrinsic understanding and for development of applications to robust processing and storage of quantum information. Now, not all of these phases that I've mentioned can be realized readily in nature. Many of them exist only on paper. On the other hand, those that do exist are often difficult to control and therefore understand fully. So in order to create and understand both types of systems, researchers in the field of quantum simulation study how to design and manipulate quantum devices so that such devices can act or simulate the quantum systems that we're interested in understanding. And in general, this is a field that's concerned with any quantum systems of interest, but in particular, a large class of this field, a large subfield or a large class of these systems include those consisting of subatomic particles and their corresponding quantum field theories. And so particle physics simulation, quantum simulation, is grounded in the idea that the quantum devices that we can engineer today and maybe tomorrow including those that can fit on a tabletop, will prove useful in modeling such subatomic nuclear behavior that large colliders may not be able to understand as well. Last but not least, quantum foundations is a field that determines sort of an axiom or studies an axiomatic understanding of quantum physics, in addition to other areas that are somewhat connected with philosophy. So let me go through the experimentalists. I'm sorry that I might go a bit over time. So I'll organize this in terms of devices. One of the key devices that Maryland has been traditionally strong at is trapped ions. This field utilizes degrees of freedom of ions that are confined using dynamic electromagnetic fields. Very close cousin is ultra cold atoms. Very close cousin. And there's lots of people around Maryland. If you're interested, feel free to reach out to these wonderful experimentalists. Microwave cavities and superconducting circuits, another key technology of today. It tries to build quantum devices out of nonlinear electrical circuits that are very, very cold. Key player here is the Josephson junction. That's an ingredient used to build lots of fun nonlinear circuits. Quantum optics research. Here are the quantum optics researchers in experimental quantum optics. And as I mentioned, the members of the Quantum Materials Center are trying to synthesize materials, make interesting materials that have interesting quantum properties. There's a large effort here at Maryland on that front, as well as understand or characterize these materials by shining light on them, or measuring or hooking up a battery to them to measure current. Now I skipped here superconductivity, which is in particular a well-established field that tries to make and characterize superconducting materials. The experimental wing of quantum sensing is here. There are people at NIST that are very interested in these areas, as well as other people at UMD. And NIST is very big on quantum networks. And so there's several people that you want to reach out to if you're interested in that on the experimental front. And I think that's it for me. So I hope you enjoyed, you got something out of this talk, and thank you for your attention.
Okay, so we have time for a few questions. So we can take questions both from the in-person audience as well as from our online audience. So as before, anyone on Zoom who'd like to ask a question, please send it or raise your hand, and Adam will see it and either unmute you or bring it to our attention. And similarly, I will call on anyone in person who has a question and repeat it for Victor. Yeah, so go ahead. Yes, one person question. Go ahead, please.
Should I just ask it?
Yeah, just ask and I'll repeat it.
So, in your opinion, what are the top 3 toughest challenges faced by society which development quantum technologies to solve? And to what extent are quantum technologies solutions to their problems?
Okay, hopefully I can repeat that accurately. So our question was what are the top 3, you said, sort of societal problems that quantum technologies might be able to address? And also, to what extent are quantum technologies a solution looking for a problem? Which you said also was the laser initially, I guess.
Top 3 societal challenges. Well, just my own opinion. In the near term future, I don't think quantum computing will be able to address too many societal challenges, but in the very, very long term, one of the challenges is simulating quantum systems. And there are many quantum systems of interest that are and various drugs and sorts. And so trying to have a better, more precise understanding of such of large atoms and molecules and proteins would be, I think, something that would make a huge impact. Now, there are already many smart people trying to understand those systems today from probably a more classical perspective than the one I'm trying to, than the one quantum simulation is pushing for. But if we can do it in the intermediate future, I think that would be one of the prime applications. Now, as I said, quantum computing is not the only application here. So I think another societal challenge deals with sensing. If we can, better dig for oil or understand again properties of small proteins and organisms by sort of connecting quantum probes to them, that would also, I think, biological sensing would be a very viable application. Those are again very hard, but I think if we can pull it off, I think it would be on par with these electron scanning tunneling electron microscopes of the past. Third application, well, I guess then that leaves quantum computers per se. If we can build a device that's precise enough to do a computation, then we'll be able to solve very specialized but very useful problems, like reading encrypted files. And this is an impact that's already being somewhat made. There are institutions that are switching to something called post-quantum cryptography, which is a set of protocols that are believed to be robust against an attack by someone wielding a very powerful quantum computer. But even bigger impact would be made if we were actually to get these devices up and running. But that's a very something that to me is very, very far in the future. Your second question was to what extent? Well, as I said, like quantum science, technology, engineering, mathematics is way broader than any one application. And so while there may be some effects that are currently kind of like in the same position as the laser, there are many that have very clear applications that I mentioned before.
Other in-person questions? Any online questions? Yeah, here's that one.
So I was just curious, how do you think the carbon footprint of quantum technologies grow over time? Is there any projection? Do you have an estimate?
Okay, so the question was, how does the carbon footprint of quantum technologies grow over time? Do we have any estimates of that? Is there some concern there?
Yeah, William, you were cutting out, but I heard the question about the carbon footprint. I don't know much about it. I do know there are people worried about it. And when you do, for example, when you do numerics, you can often report how your carbon footprint that you've left by running the supercomputers. But I can't comment anything useful about that.
Thank you. Any questions? All right, I think that will probably be it. So thank you so much again, Victor. And yeah, I think we will conclude our Zoom session again. So thanks again to our Zoom audience, and we'll see you all either in person or online again